All right, now we're going to talk about diffraction. We mentioned this at the very beginning, diffraction. What is diffraction? It's just interference, you know, but it's interference effects from many, many waves. Or another way of thinking of interference, it's when light goes through something or around something and the light seems to bend, right? So this is when light goes through something, it spreads, that's diffraction. Look at now, or you can say when light goes around something, it causes a diffraction pattern. So look at this, somebody's holding, I don't know, whatever, and what do you see? So the light is going around the fingers, right? You can see this pattern, right? That's called diffraction. This is kind of cool. So here's one of these double-edged razor blades, right? So look, actual shadow, so this is a shadow of a razor blade illuminated by monochromatic light from a point source. Monochromatic, mono means one, so that means it's probably like a laser, right? One wavelength or one frequency. So this is a shadow, right? But my gosh, what do you see? You see a pattern. You see this diffraction pattern. So here you can see it a little bit, but then they blow it up. Look at that. So this is the shadow, right? See the black right there? This is the shadow. But what do you see? You see a diffraction pattern, you know? So that's kind of cool. I mean, here's something else. So here, you know, you shine light. You have, you know, instead of having like a double slit, like for Young's experiment, you have tons of slits. And I didn't show it here, but you see a diffraction pattern. You can actually do it with your fingers. So take your, whatever, I just use my thumb. Take your thumb and your finger here and put them super close to one another, but not touching. Almost, but not touching. And look at a light. Look at a light. You'll see a diffraction pattern. So try it. It's kind of cool. All right. So let's see. So that's diffraction, right? I showed you this already. You see the bending. See how it spreads. Okay. Now what we're gonna figure out. Diffraction. So diffraction depends on the wavelength and this is called A is the slit width. All right. So A is this distance here. Okay. So diffraction depends on the wavelength of the wave and the slit width. Okay, so if I were in a normal classroom, sorry to keep saying that, all right, like let's say I was in my K132, what I would do, I would step outside in the hallway, and I'd get behind the wall so you can't see me. And then I would say something, right, with the door open. And you know, you could all hear me, no kidding, right? But you can't see me. Now the question is, why can you hear me, but you can't see me? Well, I mean, the wavelength of sound is much, much larger than the wavelength of light. So it appears that the wavelength, that sound, can somehow diffract, right? It can somehow diffract, and you can hear me when I'm outside in the hallway. However, you know, you certainly can't see me, right? Okay, so that means, so diffraction happens with large wavelengths, but not small wavelengths. So that would kind of indicate that diffraction is proportional to wavelength. If it's a large wavelength, it's a lot of diffraction, a lot of bending, you know? If there's a tiny wavelength, hardly any diffraction, there's no bending. Like light, right? Light doesn't have a lot of diffraction because it's a super small wavelength. All right, well, how about A? How about A? Well, look at this. So here's a large A, right? Large slit width. Here's a small a. Which one do you see the more bending? It's pretty obvious. Here you hardly see any bending at all, right? Here you see a lot of bending, right? So here we would say diffraction is proportional to 1 over A, right? If A is super, super small, then this is large, so this is large. If A is big, this is small, so this would be small. So that's called the inverse proportion. Remember that from algebra? Okay, so we put these together, and we just see that the fraction is proportional to or depends on lambda over A. And we're going to use that a lot too. We'll even talk about it in quantum mechanics. So a lot of the things we learn in this chapter we're going to use again and again and again. It's kind of cool. All right, so this is here's the bottom line. Diffraction is proportional to the wavelength. The bigger the wavelength, the more diffraction. But it's inversely proportional to A. We want small a gets big diffraction. Okay, in the lab, you're going to have a lab on diffraction, and you're going to use something called a diffraction grating. So this is a diffraction grating, all right? This is a piece of glass. Now, it doesn't look like it, but there's actually 600 slits per millimeter. Isn't that incredible? Doesn't look it, right? So, you know, that's what it is, all right? So it's kind of like this, right? You know, you just have tons and tons of slits, all right? Tons and tons of slits. Now, I'm not going to go through it. I'm not going to make you go through it either, but in order to figure out the interference relationships, it's very similar to what you did with the Young double slit. So it's kind of like the same logic. You know, you assume that these are parallel, and you know the interference is caused by the different path lengths. So there's a path length difference. So it's very, very similar. But anyway, here's the answer. So for constructive interference for a diffraction grating, the equation is d sine theta equals m lambda, which looks pretty familiar, right? All right. All right. Now, there you go. Now here's a question for you. So you have white light, and you have it pass through a diffraction grating, and this is what you see on the screen. Why? Look at the equation. Why do you see this? So pause your video and think about it. All right. So look at the equation. The equation says that sine theta is proportional to the wavelength, right? Well, what's white light? White light is a mixture of all the different colors. And what's the difference between one color and another color? The wavelength. So different wavelengths have different angles. And you can see that, right? Different angles have different wavelengths have different angles. So there you go. All right, so that's what you see. And that's why people have prisms hanging from their window sills or windows or porches or whatever, you know, because you can see that cool rainbow, which is kind of nice. If we were in class, I'm sorry, I would hand out diffraction gratings, and you'd each have one. You could take it and look at the ceiling light, or look at the light from a cell phone, or look at the sun. Well, that's not a good idea, it wrecks your eyes. But anyway, you could have some fun with diffraction gratings. So sorry. Okay. Oh yeah, how do you like that? That's pretty cool, huh? So this is the light source. It's the light coming from one particular element, which is heated up, so it emits light at one particular wavelength, and you're looking at that through a diffraction grating. So you're going to do that in the lab. You know, so let's say that the light source is here, and then there's a diffraction grating, and then you're over here, and so you get to see this. You get to see all these different colors. So it's kind of nice. So you get to measure the wavelengths and all this neat stuff. Well, I mean, okay. You'll do that in lab. I don't need to say anymore. Okay, now let's say we want to find an equation for Ym. Well, you should be pretty good at this by now. So, so Ym is just L tan theta, right? Because tangent is opposite over adjacent. So then you multiply it by the L, the adjacent, you get Ym equals L tan theta. So that's the same as we had before. Now you got to be careful. Now you can't be a robot anymore. So, I mean, this is true. But how about using the small angle approximation for tangent? Remember we had tangent theta is approximately equal to sine theta? Well, you could probably use that for maybe like y1, but maybe for y2, it depends on what the angle is. But, you can't use this. This is true, but you can't use a small angle approximation for like y3, maybe not even y2, it depends. So all I'm saying is you got to be careful, right? Small angle approximation is for small angles, like like 17 or degrees or less, or maybe 20 degrees or less. But anything bigger than that is wrong, you know? So this is true, but you can only use small angle for small angles. So just be aware of that. Okay. So, so in the lab, you will use the diffraction grating to measure accurately the wavelength of light, which is impressive, right? Because they're so incredibly small. Astronomers, this is called spectroscopy, when you use diffraction gratings to measure the wavelengths of light. Astronomers use this to identify elements in like outside of stars and outside of galaxies and stuff like that, because every element has a unique pattern like this, and so astronomers can use that to figure out what elements are, you know, thousands of light years away. We'll talk more about that when we do quantum mechanics. I'm just saying spectroscopy is incredibly important in science. All right, so this is a demonstration I do every semester, or every year I teach this class in one of the classrooms. And so I just have to describe it here, you know. So this is like, I usually do it in McKay 132. So this is the front whiteboard, the front of the classroom. And this is the back of the classroom. And so I stand at the back of the classroom. I just have a laser pointer. And I have a 600 lines per millimeter diffraction grating. So I just shine the light, you know, the laser light through the diffraction grating. And you see one bright line here, and then you see one bright line here. All right? So basically, I mean, it's just this, right? You know, you see the center, you see one here, and you see one here, all right? Okay, so that's what I'm saying. All right? And then what we do, we just, and we're not really super careful about this either. I mean, like, I'm just standing here holding the laser, and it's amazing, you know? You think you're holding the laser still, but you're not. You're moving it a little bit. And so this is moving a little bit, this is moving a little bit. So we just have some students take a tape measure from here to here, not being super careful. Then they measure from here to here. Again, not being super careful. I mean, try to be, you know, relatively careful, but not super careful. And it's hard, you know, because again, this is moving a little bit. This is moving a little bit. So, and you know, like I said, the laser's up here. And so it's just, anyway, we do it okay, but we're not super careful. But what you'll see is, even being kind of not super careful, we can get great results for the wavelength of light. All right, so here, so what did we just saw? What did we just see? We just saw that, right? Okay, so now let's say, all right, ready? So we're going to use, this, and we're also going to use constructive interference. So basically, we're going to use something like this. We're going to say m lambda equals d sine theta, right? So it's just what we had a minute ago. Did I write it down somewhere? Yeah, there it is. Okay, we're going to use that, all right? D sine theta equals m lambda. All right. Okay, now we got to measure everything. Okay, so from that, what is sine theta? Well, sine theta is opposite over hypotenuse, right? So sine theta is y over r, okay? And so, you know, we're going to measure this, we're going to measure that. We just use Pythagorean theorem to get that. Okay, but then there's a d, right? So d is the, come on, where are you? This is d, right? That's d. The distance between adjacent slits. So how do we get that? Well, it's 600 lines per millimeter, right? So therefore, what's d? Just the reciprocal of that. So therefore, d is just 1 millimeter. divided by 600 lines, or divided by 600, okay? And got to get it in meters, right? Because we're doing everything right, you know? And so 1 meter is 10 to the third millimeters, all right? Okay? So we do that. So, okay, so all I'm saying is that's 1. So you plug that in here, you plug that in here, and the last time we did this, all right, so last time we did this, we get 533 nanometers. And then you look at the laser pointer, so this is our result, right? Then you look at the laser pointer, and the actual is lambda equals 532 nanometers. So that's 0.2% error. I mean, that's impressive. You got to admit, you know. And we weren't even being super careful. 0.2% error. So that's why people use diffraction gratings in the real world. You know, when they need to measure wavelengths of things, because you can get incredibly precise and accurate results. I mean, they're amazing, right? Amazing. All right. Okay, now we're going to switch topics. Now we're going to talk about what's called thin films. So this is a bubble, right? And you can say that the surface of the bubble, you know, that's like it's a thin film, right? It's a thin film. Or, I mean, here's another. All right, so what's here that isn't here? So these glasses have an anti-reflective coating on them. So the coating is the thin film. So we want to talk about thin films. And anyway, let's go. All right, now let's review something that we learned in Physics 105. So here's a string, right? So this string has a different mass per unit length than this one. So we call this a discontinuity. And what we learned was that remember mu, it's the mass per length. Here, we learned about the speed of a wave on a string or a thin wire. It was equal to the tension of the string divided by mu. And mu was the mass per length, right, of the string, right? Mass per length. So we call it mass density, but it's length, it's not volume like in chemistry, you know? Okay, so look at this. So the mass per unit length over here on the left is less than the mass per unit length on the right. And it's sort of obvious, right? Just by looking at it. And what we saw last semester was that when this mass density is less than this mass density, so some of the wave, you know, keeps going, but some of it is reflected. And when mu left is less than mu right, this is inverted, right? So the reflected pulse is inverted. On the other hand, now we have mu left is greater than mu right, and there's our discontinuity. Again, when the wave passes the discontinuity, this wave keeps going, some is reflected, but look, it's not inverted, right? It's not inverted, okay? So it has to do with the mass densities. If it goes from small mass density to large mass density, inverted, large to small, not inverted. We're just talking about the reflections, right? Just the reflections. Okay, now, what's this got to do with light? I thought we were talking about light. Well, hold on. So what we care about is this situation, all right? So we're going to kind of concentrate on that. When mu left is less than mu right, it's inverted. Okay, here's a sine wave, right? Just an ordinary sine wave. So if I move that sine wave, in other words, I shift it either this way or this way, how much would I have to shift it so that the sine wave is inverted? Okay, so I mean, right here, you know, it's like this, right? I wanted to get it to go like that. So how much would I have to shift it? So just look at it, stare at it, look at it. hopefully you can see a half a wavelength, right? And either way, because if I shift this a half a wavelength, then this piece is here. Or I can this one too, right? I could do it that way. So this piece would be here, okay? So all I'm saying is, if I shift it half a wavelength, either way, you know, it's the sine wave is going to be inverted. Half a wavelength shift, inverted. Now, half a wavelength. So, you know, so it's kind of like this, right? This is inverted because of the mass densities. This is inverted because I shift the sine wave. Yeah? Okay, so what I'm saying is that the inverted reflected wave on the string is similar or equivalent to just taking a sine wave and shifting it a half a wavelength. So I'm saying, you know, like a path difference, right? A path difference of a half a wavelength is going to give you that lambda over 2 shift. So okay, that's light, right? Okay, so what does it got to do with light? So here's light. So if we have a low N here, like a vacuum, and a high N, like glass or water, look what happens. So the wave comes in, and if it goes from low to high, it's inverted, right? It's inverted, just like this. If it goes from low or small to large, mu, it's inverted. For light, it goes from low N to large N, it's inverted. So it's equivalent to a path length difference of lambda over 2. On the other hand, if we go from high N, like water, to low N, like air, air, what do you notice when it's reflected? There's no shift at all. So there's no lambda over 2 shift, so we said that the path length is 0. The path length difference is 0. Okay, now that's actually very important, all right, because that's going to allow us to solve some of these problems. All right, so that's here. Look at this. So we have n equals 1, that's air. We have n greater than 1, glass or water or something like that. Let's say glass. Then we have n equals 1. So look at the reflections. That's all we're talking about is reflections. So here's an incident beam, n equals 1. Then it reflects at an n greater than 1. Well, what did we just learn? So it goes from small n to large N. So what did we just learn? Small n to large N, on the reflection it's inverted. So you look. So here, look down here. So here's the incoming beam, the incident beam. What do you notice on the reflection? It's inverted, right? It's inverted. All right, now let's look at this one. Okay, but notice, so some of the light is reflected, some of it continues on its merry way. Don't worry about the, okay, see how the light changes the angle? We'll talk about that later. Ignore it now. Okay, so some of the light keeps going on its merry way, but then it's reflected here, right? There's a boundary, there's a discontinuity, so it's reflected, just like strings and stuff. So now it's going from large N to small n, right? Large N to small n. What did we learn? Large N to small n, no inversion. So look. So that's here. So here's the incoming, right? Here's the incoming. Here's the outgoing. What do you notice? There's no inversion at all. There's no lambda over 2 shift. Okay? All right, that's a good place to quit.